Hello everyone, I'm Bohu from NTT R&D. Today, I'm very happy to share some idea about collaboration between ISPs for cybersecurity. Actually, this is a joint presentation by Orange and NTT, so we really appreciate cooperation from Orange colleagues Cario and Fabio. And in this presentation, I will introduce a background, a problem statement, and entity's existing approach paper first. And our colleague from Orange will introduce their own system, Udo, collaborative approach, and evaluation result. So let's see the background first. As we know, a botnet is a group of malware-infected machines that can collaborate with each other to launch different kinds of cyber attacks. As shown in these figures, after downloading malicious binary from malware distribution site, a malware-infected machine will become a bot in a botnet, and the whole botnet will be controlled by command and control service. And after receiving attacking message from command and control service, those botnet will launch different kinds of attack, such as internet scanning, DDoS, or spamming. And since currently IoT-based malware has been spreading faster and faster, so the size of IoT-based botnet is getting bigger and bigger, and finally became a serious problem to the whole internet society. And as the countermeasure, we think the conventional signature-based approach has the difficulty to detect the increasing types and amount of malicious activities. And the machine learning becomes a new hope. It can automatically extract the intelligence from large-scale network traffic, and the botnet detection is one of its important application fields. As shown in these figures, to launch attack, the malware-infected machines need to look up the malicious domain name to finally get the IP address of its command control service, and then send a beacon to get attacking message. So through the passive DNS record or flow data, we can observe and analyze such kind of malicious activities. And based on different types of data, we can build different features and prediction models. And finally, for different purpose, like bot detection or command control detections. Actually, there are already many existing methods using machine learning, but those methods have been deployed in user networks. Even though with those techniques, we can detect the malicious activities coming from traffic coming from or going out to the internet. But currently, attackers tend to use layered and distributed infrastructures to control the whole botnet. So even though we can detect some lower command controls or proxies, but it will be easier to be changed. So from a holistic perspective view, we think large-scale traffic analysis at the internet backbone is necessary to understand the whole picture of botnet. And of course, internet is interconnected networks, so there are many different network operators or like ISPs to provide a different service on the internet. So to comprehensively detect the botnet, we think the collaboration between different ISPs are expected. For example, some ISP can detect the malware-infected machines, and other can also detect the upper command and control service. So by combining different detection result, it will easier to understand the whole picture of the botnet, and also as well as taking some botnet detection, botnet down. So however, this is the collaboration between ISP is also a challenge, since different ISP may have different types of data, and since the raw traffic data may include user privacy, so they cannot exchange the raw data directly. And even though different ISP will have different techniques, but those techniques which use machine learning will use some features relying on the raw data, or will use different inference model also relying on the raw data. So of course, different ISP cannot directly exchange detection technique as is. So the existing collaboration between ISP are limited to information exchange. And in these collaborations, we introduce a new collaborative framework which can leverage threat intelligence more. So as shown in these figures, let's say ISPA have its own threat intelligence and enrich features, and it can share those information to ISP, and the ISP will use those information to enhance their own prediction models, and in order to detect a new threat intelligence, and then feed those new intelligence and enrich data back to ISP. And during the whole collaborations, we don't exchange the raw data any. We only exchange some threat intelligence and enriched features regarding the malicious service. And in these collaborations, we deploy our machine learning pipeline pipers. And one of the motivation to create piper is a computational efficiency. Let's say, as I mentioned, for detecting different component in a botnet, we need different kind of detection applications. And every time we apply a new applications, we have to pre-process the data or generate feature from the data. So those overlaps in pre-processing or feature generation will become a bottleneck, especially when we apply detection application to large-scale data traffic. Of course, an efficient and practical platform for internet scale traffic is required. So that's why we create a unified machine learning pipeline there. And here is the whole architecture of a Piper. So it's our unified machine learning pipeline for internet scale traffic analysis and threat intelligence, threat detections. And first, the Piper collect the flow data from internet and pre-processed data, and then it generates all the features for different modules. And it has a dispatcher to deliver pre-calculated features to different machine learning models for different purposes, like command control detection or bot detections. Moreover, we also have a selective sampling technique to reduce data by 80%, as well as maintaining the same level of accuracy. And we also have our original features to enhance the detection accuracy. So it's fast and accurate. And with its faster pipeline and predefined capabilities, it's very easy to deploy new applications. And in these collaborations, we deploy a new detection models, which consume Voodoo data as levels to detect the new, unknown malicious data. And then we feed back those data via Voodoo API to Voodoo database. And here is some evaluation result about our pipers, but not this collaboration result. First, as I mentioned, since it unified pre-processing and feature generation, so the total processing time is fixed. Whereas in the case of deploying application individually, every time it have to pre-process data or generate features again, so the processing time for our situation is fixed, and the situation of in the case of individual pipeline will increase linearly with the number of applications. And with our predefined features, we can achieve higher accuracy. In this case, we can get higher ROCAC scores. And we also deploy Piper in the real world to hunt unknown threat. And every day it can detect more than 1,000 malicious IPs. And some of the detections are earlier than any other security vendors. And it also supports graph-based search engine to search malicious traffic recursively. So here's my presentations, and during the next sessions, our colleague from Orange will introduce their own system and our collaborative framework. Thank you.
Hello everyone, I'm Karel Mittig, Research Engineer at Orange Innovation, and with my colleague Fabien Bignon, we will present you the Voodoo research project, how it collaborates with Piper, and then our joint experimentation results. Before talking about the Voodoo project, let me say a few words about the background and origin of our work. Today, with the availability of automated intrusion tools on the dark market, attacks on the internet have accelerated to an average of few hours between the setup and the ending. In contrast, traditional defense mechanisms have remained much slower. If we consider the whole process from discovering the attack up to disseminating the signatures to the detection equipment, it takes at best several hours and more generally several days. This is confirmed by a study we made at Orange Labs in 2020, in which we found that 77% of the indicators reaching a CTI platform were already obsolete by the time they arrived. So, if we want to improve usability of threat intelligence, we need to implement threat hunting algorithms that allow us to identify threats before they impact our networks. This led us to the Voodoo research project, which seeks to proactively discover threats using hybrid AI techniques. The main principles implemented in Voodoo are the following. First, we collect all possible information regarding cyber threats over Internet through public and private information sources, blogs, honeypots, and so on. This information is normalized in order to extract usable value, and then we combine two distinct artificial intelligence systems. First, an expert system, which allows us to automatically analyze and label data, and then a machine learning and deep learning system, which can be trained by this labeled data. So the main point is that this system allows us to produce trained models and classifiers in a fully automated manner. We then use these models to continuously crawl the internet in order to identify malicious patterns and contents that are then reinjected into Voodoo. All this data are then correlated to produce actionable information in the form of technical and tactical indicators, trends, etc. Finally, a retroaction loop allows external systems to influence Voodoo algorithms through reinforcement learning. So practically, what does Voodoo data represent? Today, the Voodoo platform manages around 23 million of signatures, with a renewal rate of around 2.5 million signatures per day. By correlating Voodoo threat hunting results with external sources, we're able to estimate the uniqueness of Voodoo information, which is around 25%. Also, Voodoo allows us to classify this data by computing an associated reliability, a threat family, a threat type, etc. Okay, so now, how do we combine Voodoo with Piper? The framework we put in place with NTT is the following. On one hand, we have the Voodoo platform performing threat hunting over Internet to identify new IOCs. This information is then filtered, so we keep only active IP addresses and then send to Piper. Taking these IPs, Piper will be able to enrich them with network features in order to produce their own detection models. Then, by applying these models on the NTT backbone, Piper is able to detect new threats different from the one initially discovered by Voodoo. This information is then filtered in order to ensure that it does not contain any private data and reported back to Voodoo. Voodoo will use it both as a new source and also for reinforcement learning, thus creating a mutual enrichment loop. So we have been able to experiment this collaboration with NTT since the beginning of September, and now I will leave the floor to Fabien, who will present you our main results.
In 1 month of experiment, Piper detected 652 distinct IP addresses. 120 of them were unique entries. The reliability computed by Voodoo shows that more than 60% of detected IPs have a good probability of being malicious. Several IPs have no domain associated, and several of them are dynamic. 11% are probably false positive or have a high probability to raise false alarm, mainly because most of the time these IPs are used for virtual hosting. In addition, 209 IPs were reported first by this collaboration with an average of 9 hours in advance. Concerning IPs known by Voodoo, results show that an average of 11 sources were reporting the same IP. It's a pretty high number of overlap for threat intelligence, and among the overlapping sources, several of them are highly reliable. At the bottom of the slide on the left, you can see the top 5 out of more than 60 sources overlapping Piper detection. All those results can be used to validate detection provided by this collaboration. Piper Live malicious traffic detection provides additional features along with the IPs. For example, port numbers. Port numbers help to extend knowledge of the malicious activities, to be more specific about the malicious activities, and to enrich Voodoo. Piper provided more than 500 new ports during the experiment, from registered ones, such as HTTP, which is number 1, followed by SSH, to unknown private ports. At this point, we are detecting malicious IP with features. Voodoo uses computed features, included Piper data, to process classification and to associate to each IPs a threat family. You can see the main threat family on the left. Results show botnet-related activities such as Trojan or malware and command and control server have been detected. On the right, Voodoo computed threat names. If most of the threat names cannot be determined at this point of this experiment, the first threat name detected is Mirai, or Mirai-like threats, validating the botnet-related activities again. More than 90% of detection are targeted IoT devices and Unix systems. Another side of this experimentation helped to improve 2 key features when it comes to threat intelligence, namely lifetime of indicators and reliability. Reinforcement process of Voodoo can leverage features provided by Piper to correct false positive and false negative. Regarding false positive, on Voodoo side, indicators of compromisions were classified as false positive initially, mainly because no feed was references these IPs, or Voodoo has no longer information enough to classify them. 18% have been reclassified as malicious and as active through this process. False negative correction is also an interesting result through this collaboration. Voodoo classified IPs with a low confidence, mainly due to the lack of source references there. In that particular case, the collaboration helped to enforce the reliability of more than 70% of the indicators with a low confidence initially. This is an important result, since avoiding false negative is a very difficult task. To summarize, this experiment shows a new way to create threat intelligence by combining 2 distinct threat intelligence approaches. First, Voodoo provides to Piper blacklist of its threat entities, composed of unique IPs. Then, through Piper processes, new IPs have been detected along with features. Voodoo had classification and context for them and computed a reliability. Both threat intelligence approaches benefited from each other and produced an actionable feed that can be disseminated towards detection systems such as firewall or antivirus. In conclusion, the collaboration between NTT and Orange have introduced a new approach to share, enrich, and extend threat intelligence. It also preserves the privacy and confidentiality of communication. The first results indicate this collaboration enables the detection of new command and control server and botnet-related activities. It then allows to produce an actionable feed. Regarding perspectives, This collaboration shows new opportunities to improve cybersecurity among Internet service providers. It could be extended to detect other malicious activities in the future as well. Thank you for your attention and feel free to ask any question.
Let's get to our question and answers with Bo, Carol, and Fabian. The first one we had, and we're going to pose this one to Bo, from Mike asking, are the data sets from the internet ingest into Piper raw packets, standard net flow, other formats? Thank you. Bo, to you.
Okay, thank you, Mac. I think the format is NetFlow v5 or v9. According to the scalabilities, we cannot consume a PCAP directly, but if there is any good tools, we will think about that. And I think there is another question also from Mike. It's question 4. He mentioned that whether we are currently sampling the data or not. The answer is yes. Due to that the limitation of storage and network bandwidth, currently we are sampling data. The sampling rate is 1 out of 10,000. Thank you.
Next question was from Josh, and he asked, is this the same as the Piper repository on GitHub? If not, are you familiar with that? And can you speak to that, how they differ?
Actually, I'm trying to seek the Piper repository on GitHub, but I didn't find that. If you can kindly share the link, I can tell. Maybe I can tell the difference. Maybe maybe offline, but
yeah. So maybe that's a good one to add in Discord, and we can handle it there. That's
yeah, please. But I really appreciate that question from Josh. But we didn't open the source, but we published the paper about Pipers. So if you are interested about that, I can also share the link of IEEE page.
Then we had another follow-up question from Mike. Is are there more features from PCAP you would anticipate being useful to ingest beyond NetFlow?
There could be, but as I mentioned, how to say, due to the limitation of the scalabilities, currently we are only focused on NetFlow data, but we still have other like separate object project which also focus on some payload from PCAP. So in that case, we will use more data. For example, in the case of headers, we can use some like window size or some other like information not included in NetFlow. And in the case of the payload, which is not encrypted, we can also just try to see some like contents inside the payload. But I think NetFlow has two advantages. One is scalability, and the other is privacy, because it doesn't like inspect any payload data for any users. Sorry, probably my answer is too long, but the answer is we have another project which focus on payload, but in our project, due to the scalability of internet scale traffic, we only focus on NetFlow data.
Great, thank you for that. Next one, we'll open up to the three of you. Is a question from Jim asking, did this collaboration come about because of Flowcon?
So not directly. In fact, we started to work with NTT on the research side in order to check our respective work regarding botnet detection. So I say not that directly because as I remember, Bo presented Piper already 2 years ago at Flowcon. And so it was an opportunity for us to see that work. And we saw that there were a way to work together, even if we are taking data in a different way. So we were able to build up something together in order to detect botnets better.
To the next question is kind of related to that. Since this did come about from collaboration, how would you guys recommend people go about finding interested collaborators and getting relationships off the ground? Any advice there?
Yes, this is a really complex question, really open. So the first point, I think, and this is why we are presenting that works there, is first to present and to show up what is possible to do and the interest we have in doing so by sharing information. So I think the idea of this presentation to Flowcon is to give people ideas about such collaboration, the kind of benefits we can take from that, and therefore how we can work together in order to find relationships between the way we are working and what it can bring overall.
That's a great answer. Come to FlowCon, meet people. That's it.
Yeah.
Any parting words from you guys? We're down to about 2 minutes. Anybody with any closing thoughts? Otherwise, we're going to turn it back over to Josh here in a minute, but I'll give you guys the floor for about 30 seconds. Anything to finish up with?
Thank you so much. And I think we really appreciate the Flowcon to provide a good chance to not only share the presentation or ideas, but only have a chance to talk with people. So thank you so much.
Great. Thank you three again. We appreciate your time and expertise.